Okay, so this is the second tutorial for ECE297. And this time we'll be continuing with STL. Last tutorial, remember we covered C++ templates and part of the STL library, which part of the containers library, vectors. And today we're going to see iterators. What is an iterator? What operations? What does an iterator do? What is a list and how is the list different from the vector in terms of iterator? Definition of an iterator. An iterator simply it points to an element in the container. It's similar to a pointer, but it's not a pointer. It's a class. The iterator allows us to access an element in the container similar to a pointer. It allows us to move between the elements in the container with similar to pointer arithmetic. And it's restricted to efficient operation. This means that many operations for iterator are not defined because they're not efficient enough. So they're just not implemented. And this depends on the type of containers using. It's defined for. Iterator versus the operator square bracket. Remember for arrays and vectors, we're able to use the operator square bracket to access elements with O1 time. And this implies random access, which means that given the starting pointer for the container and given the index, you can access it basically by adding the starting pointer with the index and access in O1 time. But this is not supported by all data structures. But in the STL, all containers have iterators defined. There are different types. So we have for vectors, vector templated type and iterator. We have a different iterator for each templated type, even for the same vector class, vector container. And we have a separate iterator for list integer, for example. Vector functions, we covered these ones last time. So for accessing with random access, we have the operator square bracket. We have insertion and we have querying the size. And all of the above take O1 time. And today we're going to cover iterator. The begin returns an iterator to the first element. The end returns an iterator to the element following the last element. So it points to a now element that's at the end. And this is used for bounds checking, used for checking whether you're out of bounds. So for, say this is a vector from index 0 to index n minus 1. The begin points to the first element. The end points to one past the last element. So the end doesn't really point to any valid element. It's just there to tell you that this is the end. Operating on pointers, we have a vector of integer with 4 elements, 1, 2, 3, 4. Let's see what each case does. Case 1, we define an iterator for the vector int class, it, equals to number of begin. Is this allowed? Anyone wants to answer? Show of hands, who thinks this is allowed? Okay, we have, who thinks this isn't allowed? That's one. Okay. This is allowed because we are defining an iterator type that points to the start of the vector. Case 2, IT equals 5. Is this allowed? Who thinks this is allowed? Who thinks it's not? Case 2, who thinks it's not allowed? It's not allowed because 5 is an integer. It's not an iterator. An iterator doesn't store integers. IT++, is this allowed? Who thinks this is allowed? Who thinks this isn't allowed? Yeah, this is allowed because it will point the iterator to the next element. Case 4, IT minus minus. Who thinks this is allowed? Who thinks this isn't allowed? This one is allowed because it will point to the prior element. For the vector. Case 5, we are dereferencing IT and saving into integer x. Who thinks this is allowed? Who thinks this isn't? This is actually allowed because dereferencing the iterator will get the value stored at that iterator, which is an integer in this case. So these are actually similar to pointer. Case 6, IT not equal to number sort n. So this is checking the condition. Who thinks this is allowed? Who thinks this isn't allowed? This is again allowed because it checks if the pointer points to some element. In this case, it checks whether it points to a valid element because if it's not equal to the number dot end, it has to point to somewhere inside the vector. IT less than number slot n. Who thinks this is allowed? Who thinks this isn't allowed? This is allowed because it checks if the iterator is pointing to something before the end. Dereferencing IT equal 27. Who thinks this is allowed? Who thinks this isn't? See, this is allowed. It modifies the element at IT. Also similar to pointer. Now, IT equals numbers that begin plus 2. Who thinks this is allowed for vectors? Who thinks this isn't allowed for vectors? This is allowed for vectors. This will point to the third element in the vector. And this is because vector supports random access. And looking through the vector, you have two options. One is using indices. You can start from the first index, I equals to 0, to 1 less than number slot size, and increment. Using iterators, you can start from the number slot begin iterator until the end and plus plus IT. And you can access everyone by dereferencing the iterator. And we should never actually reach numbers at end. So it's a not equal to here. Or you can use less than. Now, for the first exercise for this tutorial, let's write the function to extract the negative numbers from integers. So we have the vector of integers and a vector of negatives. We want to loop over the integers vector and add the elements that are negative to the negatives vector, and then return negatives at the end. Let's split into groups of 2, or if you want to work along, it's fine. Get to this URL here and complete exercise 1. Again, you can test it and compile and test it, but on your own, and we'll be back in 4 minutes. Now we want to use iterators to loop over the vector. And the syntax is like this. Anyone needs more time? If no one's saying anything, I'll continue. So this is what the code should look like. For loop, vector int iterator, it, points initially to integers.begin. It doesn't go to integers.end and increment every time. And if the referencing it is less than 0, which means it's a negative value, we push back the value into negatives and return negatives. Now, if we want to erase the negative values from the vector, we can do similarly, the similar for loop, and is dereferencing the it is less than 0, we can call the erase function to erase it. The erase function is defined in the vector class, and it takes in the iterator and returns the iterator, which is next to it. So it returns the next iterator. And in the case of not erasing, we do it++ in the else. Yeah, erase iterator will return an iterator to the next element after the erase. Yeah. Iterator, only the iterator. So in this case, we're not incrementing in the for loop, we're incrementing in the else. What does erase do? How's it implemented, and what's the time complexity for it? Say we have the list of process elements and we have the list of unprocessed elements. We found a negative value here, and the iterator points to here. We want to erase it. So first, we copy the process elements. We still keep the process elements. And we copy over all the unprocessed elements after here. So we do a one-on-one copy of the unprocessed elements. And we'll return the it2 to the first element here in the unprocessed elements. Does this make sense? So that means that for the erase function, the complexity is O(n) because we have to copy over all elements after the erase element. Then for the remove negatives function, what's the complexity for this one? So we know that erase is O(n), and we are looping through from integers.begin to integers.end. Complexity of remove negatives. Yep. Yeah, it's n squared. Because we're always looking at the worst case or the average case. If we have a vector that contains all negative values, this means that we'll need to do O(n) for O(n), and that's n squared. Now let's look at the same function for the list class. The STD list is a doubly linked list that can go to the next element or go to the previous elements. And in this case, it's allowed for bidirectional access. And even though it's very slow to access a single element in the list with an index, the insert and erase are very fast because we only need to update the next and previous for the neighbors. So this is a comparison for vectors. Getting the begin, end, and pushback and size are all O1 time. Operator square bracket is not available for list. Erase and insert. Vectors take O(n) and list takes O1. This is with an iterator. So erase and insert to somewhere inside the vector or list. And the iterator type are defined for vector. It can do random access, which means that IT plus 5 is allowed. For list, it's only bidirectional, so we can do plus plus minus minus, but not IT plus 5. And so that means that we have these categories for the iterators depending on the container type. First one, for random access, we have the vectors. So in this case, we can do the dereferencing of iterators. We can do plus plus minus minus plus 5, IT plus 5. For the bidirectional, like lists, we can do the dereferencing as well, plus plus minus minus, and that's it. For the forward list, remember list is bidirectional. We also have a single direction forward list. In this case, it can do the dereferencing and only plus plus. So it doesn't do decrement. Is this good? With iterators, it's then very simple to replace vector with list if while you are writing your code, you decide that this container is not working. With iterators, you can simply just replace the vector with list. And because the IT plus plus and erase are both existing in both classes, and this code will work. Just replacing vector with list. And this is one reason why iterators are useful, because it's easy to switch from containers to containers. And with list, because the erase function is O1 time, the remove negatives is O(n) time. But you just need to be careful that not all code works interchangeably with all containers, because sometimes some operations are defined for some type of iterators, but not others. So while you're doing the exchange, you should know what you're doing. Now, in C++11, it introduces the auto keyword. So instead of specifying a type such as int or some classes iterator, we can use the auto keyword. So then the compiler will determine which type to allocate for that variable for you. Using auto can help you save on typing, and you don't have to always define the class for the iterator. You can just do auto, and then the code will compile when you switch types around frequently. But you should always know what the actual type will be, even using auto. and the type is still static, which means that even if you're using auto, it doesn't change dynamically during the runtime. So you should always know what the type is, because this is kept throughout your program. And using auto can also sometimes make your code harder to read. So still keep an eye on that. So simplifying the iterator code with auto can then look like this. So for the for loop, instead of specifying the vector int iterator it, you can use auto it. So this shortens the line for the for loop by a lot. And then everything else is kept the same. And you can simpler still, we have the range-based for. Say we have a container like a vector. We can use this syntax for auto reference item within numbers and cout item to the end. So what this does is that it auto reference is actually dereferencing of the iterators inside the numbers. So then it will automatically go to the first iterator inside the numbers called item, and you can see out the value without dereferencing the iterator. Everything is done by the for loop. This is a compact syntax for looping over an entire STL container. And this doesn't only work for vector, this works for all types of container. Yeah, basically what I just said. Auto tells the compiler to automatically determine the type, which is int reference here. It loops from dot begin to dot end iterators within the container, and the item is referring to each object in the container that's already dereferenced. The first demo is on vector and list erase example. And I forgot to mention this last time. In the labs, I'm seeing that many people are opening VS Code by going to the applications and programming and choosing whichever VS Code here. You're not supposed to do that, because then it's going to open a different version of VS Code that might be not supported for the repos. So what you need to do is actually in the terminal cd into the directory that you're working with and do code period. In this case, VS Code will be configured correctly with your makefile and everything. So for the demo, then let's read the code. We're defining a vector with a lot of elements, n elements. We load the vector with n random integers. So we set the random seed here and we randomize every element inside the vector and remove negatives. Then in the list arrays, we do the same thing. Instead of vector, we're doing list. And everything's the same thing. So in VS Code, you can go to the makefile extension to compile. So this makefile will compile both files together for me. And I'll time the 2 execution times. Let's do vector erase first. Remember, this is O(n) squared. (19.11 seconds) for O(n) squared. And let's do list erase. 0.08 seconds for O(n). So always avoid O(n) squared unless absolutely necessary. And that's it for the first part. Anyone needs a break, or we can just continue? Yeah.
The value directly integer variable, for example. Can you do like casting it right in on a bit trader and then put it into that?
So iterators are actually objects, like they're classes, they're not of a single value. So you can do the dereferencing because the dereferencing operator is defined for the iterator of class. But it's actually a class, so you can't just assign any number or anything into the iterator, even with casting.
All these were in dispute. What was it called? Forms that you just
The range-based form.
The first variable is always the equation.
The auto reference item inside this container will always go from the container's begin iterator to the container's end iterator.
So like the thing we use to go through it's always the iterator, it's not just be like a simple.
It's a value. It's a value because you're using auto reference. So the range-based for loop will just, it goes to that iterator and dereference it and gives you the reference to that value. So that it's not an iterator, it's not a pointer, it's the actual value. And you can set it in.
Yeah. The timing command you use, does that work for any program? If you just write time and then the name of the program?
Yeah, that's a Linux command. It works for every program. Anyone needs a 5-minute break, or we can just directly go to the second half. Okay, that means good. I'll directly go into the second part, which is some other containers in the STL. We're going to cover associative container, sequential container, unordered associative container, ordered associative container. So if we want to find a value in the vector container, option 1 is to use the scDefine function defined in the STL. And this scDefine will loop from the iterator begin to the iterator end until you find the actual value. This find function is defined in the STL, so you don't need to write it. And this function has O(n) complexity. So if it finds the value, it will point the returned iterator to the iterator pointing to that value. If it doesn't, it will return vector.n. Option 2, we can sort the container and then search more efficiently. For example, if we have a sorted list or array or vector, we can use binary search, and binary search takes log n time, right? But this is difficult and error prone because you need to sort the container first, and if you forget to sort for any one of the iterations, it won't work. What data structure is in? And also, if you need to sort the container first, you have to make sure that the sort is not taking too long time, because usually sort takes O(n) log n time. So that's even slower than O(n). So only use this if you're just sorting once and then you do a lot of queries. What data structure is inherently ordered? We have the binary search tree, which is covered in TUT44. And in the STL, it's called a map. So maps are binary search trees. So the benefits for the map is that it's a self-balancing binary search tree. So you're guaranteed a low O log n time for find, insert, and erase. And this container will balance itself, so you don't need to worry about having a very unbalanced binary search tree. The map uses pairs to store its values. So the first is the key, second is the value. For example, domain name lookup, which is used for your browsers, for your networks, if you need to access a link, a URL. In your domain name servers, it's stored in a binary search tree where the key is a string and the value is an integer, which is the IP address that you're going to. And this is stored in a pair. So using the map, we first obviously need to include the map container. And then we define the map where the key is strings, value are integers. And we have 3 options of inserting into the map. The first option is that we create a pair using the pairs constructor. And then we insert the pair. The second option is that we make a pair using the scMakePair helper function. So this make pair helper function it's not a function inside the pair. It's a helper function that's global in the STL. And then after make pair, it will make a pair that's of this type. So in this case, you can save it into an auto type. And this saves much typing. And then insert the pair. Option 3, you can directly insert whatever is returned from the make pair. This saves some more typing. Now, searching in the STD map. We have the map with string and integer for DNS lookup. And we inserted 3 pairs of URL and IP address. Now, if we want to look inside the DNS, what should we use to search? Should we search for the key or the value? Key. We search for the key, which is the URL, the string. And how do we check if the key was found and if it was not found? So the find function will return DNS lookup.end if it's not found. And if it is found, it will return some iterator to the actual place where the key is found. So because we have the iterator, we use this to access its first and second values because iterators needs to be dereferenced. Yeah. This one? This is just simplifying the iterator definition. So we know that this is returning an iterator. And because it's returning the iterator, we are accessing it like accessing a pointer. And if it's not found, it will point to the end iterator and we'll just print it, put not found. Yeah, so the iterator points to the node in the map, which is a pair. So we can access the first and second for the pairs. And now for the second exercise, we want to iterate over an STD map. So you should use iterators and the for loop to print out all the nodes in the STD map. It's the same URL, just go to exercise 2.h and complete it. We'll be back in 4 minutes. And let me know of any problems. Any one of the for loop is fine. Like the original for loop with iterators and the granted for loop. So this should resemble what you just wrote. We auto an iterator that points initially to the begin and we increment until the end. And we output it.first and it.second. And the output will be this. So the output should sort by the key. So the map iterator is an in-order traversal of the binary search tree. And in-order traversal means that we are doing the left first, and then the center, and then the right, which means that the outputted list should be already sorted. Because for the binary search tree, the left is always less than the center, and center is always less than the right. So the mymap.begin is the leftmost node, and mymap.end is one after the rightmost node of the binary search tree. And find will go from begin and do an in-order traversal until it finds the item. If we have duplicate keys inside the map, like in this case, we have 2 John Smiths. When we query, when we insert, the map won't let you do it. So when you query, it only queries the first value. So we lost the second value. Then what do? We go to the C++ reference website and we look inside the containers library and see, are there other containers that can satisfy what we need? And then we find multi-map. For multi-maps, an insertion can take place even if the key already exists. And then we find John Smith. Arbitrarily, we only return one entry. But if we read the documentation, because find always returns a single iterator. But if we read the documentation online for multi-map, we see that there is something called equal range. And this will return the range of iterators. So you can query from range.first to range.second. And we can return the range of iterator because it's a binary search tree. So the same keys are always stored together, iterators, in terms of iterators. So this will return the iterator to the first in the range, and the second will return one past the last element in the range, if that makes sense. And querying this will output both John Smith. So what this returns visually is that when we are returning the range for equal range, the range is a pair storing two iterators. Range.first is the first one in the range, the first John Smith. Range.second is one past the last John Smith. So the for loop will go from the first John Smith to one before the second. And that's the two John Smiths. Is this clear? We have other containers in the STL that you can play with. A map is a binary search tree, so it takes O log n time to find, insert, erase, and use it when you need the keys to be ordered, and it's easy to query. Multi-map is similar to a map, and use it when you have duplicate keys, because maps only support distinct keys. We have the unordered map, which are O1 times for find, insert, erase, and query. Use when the order of keys does not matter. So you don't need to always keep the keys sorted. Unordered maps are implemented with hash. We have the set, which has the same find, insert, erase time complexities. Use when you only need keys and not their values. So a set is a tree. These are all the trees container. We have the queue. And this gives you first in, first out semantics. So when you just need to form a queue. So you want the first item that you pushed in to come out first. Priority queue will keep the elements ordered. So if you want to fast lookup of the largest or the minimum element. So priority queue takes O log n time to push, but if you just want to know the maximum or the minimum element, you can use all one time. A stack does last in, first out, or first in, last out. And a DQ is similar to a vector, but can be faster if there are frequent insertion and deletes. So a DQ is just used interchangeably with a vector in case you need to insert and delete often. A map versus unordered map. So remember, map is a binary search tree and unordered map is a hash table. So the binary search tree finds an element by key in all log n time because it needs to traverse through the tree. It's always sorted, and it can use the key type value type if key type defines the operator less than, because it uses the operator less than to compare the values of the key. Unordered map is a hash table. It's not sorted. You can use the unordered map key type and value type if the hash function for the key type is defined. And the hash function gives you the index into the hash table. If you still remember what hash tables are. And this means that unordered map is much faster because it's all one time. For this course, the standard template library is massive. We can't teach it all to you, but it's very useful if you can learn how to find whatever you need inside the library. So we have the references here, and there are more great examples online. And we have Piazza as another help resource. Now, demo 2, map and unordered map example. Code, so the other code. See, we have two files, map search and unordered map search. And two. So we're doing the same n, the number of n, and the only difference is that we are using map for one and unordered map for the other one. Everything else is the same. It populates randomly, populates the map and then randomly searches for keys. Let's compile it. And let's guess which one is faster. Which one is faster?
Unordered.
Unordered is faster because it's all one. And the map is O log n. So O1 is faster. And let's time it. Map search first. 1.99 for O log n. Then unordered map, 0.67 for O1. And this is, yeah, about what should happen for O log n versus O1. Because O log n is good enough for most cases. And that's it for the second one. We have a third one. A very short third one, and we're done. STL algorithms. So what we have been covering was STL containers. STL algorithms is another part of the STL library. And we're covering what algorithms are provided by the STL, how I can basically use algorithms to find a specific value in a container. How can I sort a container? How can I find the information I need to use the STL? Finding elements, as we just have covered, you have a collection of data typically stored in some container. You need to find a specific value in the collection. And option 1 is to write a for loop and go through each element. On each iteration, we compare the current value with what you're searching for and finish when you have found the element. Brute force. ON. Option 2, we can use the STD find. And STD find will internally use iterator to search from the iterator beginning to the iterator end. This requires less typing and less reading if you need to read the code you wrote. And it states your intent in the name of the function is that you need to find something. You don't have to read through the code and, oh, you need to find something. And this reuses the well-tested code written in the STL. So you're confident that this code will work. And find is a function defined in the algorithm header. So we include algorithm header and use std find. For the std find, you give the beginning iterator of the collection and the end iterator of the collection, and the STL algorithm will just search it for you. And lastly, gives it the value you're searching for. Compiler will determine the type if you use auto. This saves on typing, but you need to know that this is an iterator. If find fails to find a value inside the list, it will return collection.end. So if it doesn't return collection.end, it means that it finds something and you can just print out whatever is found. Now the third exercise, use the find function and iterators and make sure that only the first element is 1. So what we need to check is first, check if the first element is 1. And second, check that only the first element is 1. The other elements in the vector are not 1s. And let's go to the code word and complete exercise 3. Yep. Okay, anyone needs more time? Need more time? Okay. Good. Anyone needs more time, or I'll continue. Okay. So this code, we first get the first element from the collection, and then we use find to search for first element plus 1 until the end for 1. So if the first element is 1 and IT returns collection.end, that means that only the first element is 1. Anything else, like if the first element is not 1, or if IT is not returning the collection.end, that means that 1 is not the first element or is not unique. Is this good? Clear? So some other examples from the algorithm header. We have min, max. Those are returning the smaller or the larger of 2 given values. We have the sort that sorts a range into ascending or descending order, depending on the arguments you give. It's defaulted to ascending order. Find finds the first element of a given value in the range. So find points to the first element found as an iterator. Swap swaps the values of 2 objects. Count counts the number of elements of a given value in the range. The range is given still by start and end iterators, and many, many more. All of them are templated. And now, as an exercise of researching in the SDL, let's take out your phone or laptop or pad or anything. Find the STD sort function online and see if you can answer these 4 questions. I'll wait for it. First question, how many arguments does the STD sort accept? Yep.
3.
3, and what are those 3?
Beginning of the range, end of the range, and then the predicate functions. Like the sorting function.
The sorting function? The sorting itself is the function.
Like to decide which 2 values place before next.
The sort, simplest sort requires only 2 arguments, which is the begin and end iterators. Because sort is itself a function defined in the STL.
There's another version of it.
And there is another version of it. Yeah. The simplest one takes 2. And it has multiple versions that you can use if you need them. What are the requirements placed on the arguments? Of which type should the arguments be? The arguments. Yeah. Yep. Iterators and which type of iterators? And specific to the sort function, does the sort function require the iterator to be random access or bidirectional or incremental or?
That's like the first. Or did I do the last one?
Yeah, you can search for the sort function and it has it there. Do you have it? Do you have the answer?
Random access iterator.
Yes. They must be random access iterators for sort. And this is because sort needs to perform random access operations. How are the elements compared by sort? It uses the operator less than, which is similar to the comp function, but it's just specifically written for the template type that's used. And what is the complexity of sort?
And log n.
And log n. And that is how you should be finding what you're using. Now, if we want to sort and print a vector, then how should we call the sort function? Anyone? So we have the vector, and we then use directly std sort numbers dot begin and numbers dot end. And this will sort the numbers in ascending order by default. If you want to change it to descending order, you should be specifying the operator for comparison. For numbers dot begin, numbers dot end, total IT, and we use this to output the resulting vector after sort. And you can test this piece of code and see what it's doing, and play with the sort function to see whether you can change the order of the sort or anything. And that's it for today's tutorial. Any questions? I'll be here if you have any questions. You're good to go.